When solving logarithmic equations, the first thing you have to do is compact all the logs on one side of the equal sign, or on both sides of the equal sign, into one log, if possible. In this case, both of the two logs that I have are both of these guys, this one, and actually this one also, are all base 10, so I can easily combine together this log and this log. Let's see how. Well, we're going to use the product property. And the product property says that if I have the log of one log plus another log, then I can combine them together. Oh, but first, before I do anything, I got to get rid of this too. So let's do that. We'll use the power property to make that into the exponent of the 3. And then we still have log of 2 over on the other side. And then now we can use the product property to combine together this log with this log. So let's do that. So that gets us 9x plus 45. Now the reason why it's 9x plus 45 is because when I have one log plus another log, I get one log with the two arguments multiplied together, and 9 times x plus 5 is 9x plus 45. Now, for those of you who think you're kind of spiffy, you probably would just skip this step and go right to the next one. Please don't skip this step. It's very important that you include the step where you write both the logs on both sides of the equation, even though we're about to throw them away. You'll see why in my next example. So for now, we get to throw away the two logs. We get to throw this guy away and throw this guy away because they're the same base. And there's a property of logarithms that says if the log of something is equal to the log of something else, and they have the same bases, then it's just something equals something else. So let's write that out. And from here, it's just a simple linear equation. So it's something like 9x equals negative 43, and x equals negative 43 divided by 9. And let's see here. That's let's see here. It's a little bit more than 6, right? Because 36. I mean, it's a little bit more than 4 because 36 over 9 is 4, so it's negative 4 and something. And it turns out that that is just barely a legitimate solution. This is something like negative 4, and then after the 36 we have about 7/9 left over, something like that. Now, that just happens to be a valid solution. If that was negative 5 or greater, then we would have a problem because the argument would become 0 or negative, and if the argument is 0 or negative, then we have an extraneous solution and we'd have to throw it away. This solution, however, is legitimate because it does not cause any of the arguments to be 0 or less. Let's move on. To solve this equation, we're going to do this. We're going to start with the same idea. We're going to go ahead. In this case, we'll use the quotient property because it's a log minus another log. But again, we're going to write out the log. We're not going to just throw away the word log. The quotient property says that if I have the log of something minus something, then I end up with just the log of this guy divided by this guy, the arguments divided by one another. So let's go ahead and write that out. And this is one big argument to this log right here. And notice again, I have no number here, so we'll assume that that's a base of 10. And then over here, we're stuck with a 3. Now, some of you may have gotten into a bad habit of throwing away the log from examples like the last one. Here, we absolutely cannot because we don't have a log on this side. But one thing we can do is something called do the snail. Now, what's this whole snail thing about? Well, the snail is one way to memorize how you can convert a logarithmic equation into an exponential equation. So let's see what it involves. First of all, we start at the base, which in this case is 10, and we go to the 3, and then just like a snail shell, we go up and over, and then we go back down to the argument. And essentially, what we get is what looks a little bit like a snail shell. And so that's why it's called do the snail. And now how does it help us to get an exponential equation? Well, let's see about that. Well, exponential equations start off like this with the base, 10. And then the next thing is we go and we raise that to the power of 3. And then the next thing we do is we go and we set that equal to the argument. So that is equal to x minus 3 divided by 4. So from here you can see that we now have x all by itself, or close to by itself, and we just got to do a little bit of old-fashioned algebra to get it by itself. So let's finish this off. We'll multiply both sides times 4, and we get x minus 3 equals 4 times this guy is 4,000. So that gets us 4,000. And then in the end we get x equals 4,000 minus 3 is something like 3,997. And again, we always must check, does that give us an extraneous solution here, or there is no log here, so we don't got to worry about it. But does this guy make our argument equal to 0 or less? And in this case it does not. And here we don't have to worry about the argument, there's no x. So this looks like a legitimate solution. So we'll just box that answer and we'll move on to the next. Alright, so let's take a look at solving exponential equations. Here we have an exponential equation. This guy is a power with an exponent, and there's an equal sign. So exponential equation. The first thing we have to do is we have to isolate the exponential part of the equation, and we will do that by dividing both sides by 2. And when we do, we end up with e to the 3x equals 7 halves. And then the very next thing we want to do is we want to convert this entire equation into a logarithmic equation. And the way we're going to do that is, well, you guessed it, do the snail. Now again, what is this whole snail thing about? All it is a way of memorizing what order to convert the exponential equation in to get it into a logarithmic form. This guy is known as exponential form. We want the equation to be in logarithmic form. So what we do is we start off with, we go from the e to the 7 halves, just like we did before with the log, and then we go from the 7 halves to the exponent, which is 3x in this case. And you'll notice that again we get this neat sort of snail looking thing going. And then when we go to write this as a log, this is what it looks like. We start off with the word log, and then the next thing we do is we take this guy, the base, and we write it as the base of the log, in this case little e. And then the next thing we do is we write we follow the arrow and we write the 7 halves as the argument of the log. So the argument of the log is 7 halves, log base e of 7 halves, and then we write the equal sign, and then finally we follow the snail all the way to the exponent, and when we get to the exponent we write the exponent over here as 3x. One thing I want to remind you is that logarithms are really just exponents, and you'll notice that this log is equal to the exponent of the exponential here. And again, you'll notice that the two bases match. The e here is the base, e here is the base, and the log is the exponent of the base. And really the way logarithms work is that this exponent of this base will always be this result. In other words, this exponent of this base will always be this result. In other words, the logarithm and logarithmic equation and the exponential equation, they're equivalent. They're just different forms of the same thing. However, the nice thing is here we ended up getting x almost all by itself, just by converting from exponential form to logarithmic form. And you'll notice that doing the snail helped us out quite a bit, right? Boom. So now, one thing you might notice is that usually in math class we don't write log base e. Instead we write something else. So let's write that out. It's going to be ln of 7/2, and that's equal to 3x. And then we can divide both sides by 3, and what we get is x equals ln of 7/2, and that's all divided by 3. And if you get out your calculator, you can do the math and finish this. I'm going to leave the answer in this form. That's it for this problem. All right, let's solve one last easy one using the snail. What you'll notice here is that we have a logarithmic equation with a natural log. And don't let this scare you. There's no big deal about this. A natural log just has a base of e here, and e is just the number 2.7. Don't forget that. Just remember that e is approximately 2.7. It's not exactly, it's 2.718, and then the digits go on to infinity, just like pi. E is an irrational number, but it's approximately 2.7. So this ln means log base e. Now normally you don't see the little e written there, but I'm writing it there so it can help you. So ln means log base e. There is no such thing as ln base e. Please do not misinterpret this. Now I only write it here so we can do the snail. So let's do the snail. So we start here at the base, we go to the other side, and then we come around over the top and we go to the argument. And again, the reason for the snail is just to help you remember how to convert from logarithmic form of an equation to exponential form. So let's see what this guy looks like in exponential form. It'll be e to the power of 3. Remember, we're just following along this arrow, and then that is equal to the argument, which is x plus 7. So that's equal to x plus 7. Remember that this is just a rewriting of the thing above. This is the equivalent expression or equation to this logarithmic equation here. They're just two forms of the same thing. But this guy lets me have x all by itself. So I can solve this guy pretty quickly. And all I have to do is make it x equals e to the 3rd minus 7. Now, if you have a calculator, you could calculate out what this is. It's approximately 2.7 to the 3rd power. But I'm not going to bother with that. For me, it's okay to leave this answer for x in terms of e. You might recall from geometry class, sometimes we would leave the answer in terms of pi. In this case, we're leaving the answer in terms of e. The main thing to take away from this is that you don't need to be scared of ln, and ln is not the same as e. E is approximately 2.7. ln is really like log base e, and I'm going to write that one time so you can see it. So here you can see that ln is really equal to log base e. Please don't even look at this little e there. In fact, I think I'll erase it so that we can't see it anymore. So there you go. ln is really just log base e. But notice ln is not e. E is 2.7. ln is log base e. All right, I'm going to leave it at that. Hopefully this has been helpful.